That was a great presentation. It is really interesting to think about the future of communication. Just knowing from where we've come from to where we are today, I mean, everybody has cell phones in their pockets. So, really interesting topic. Next, I'll introduce to you Sean Cross. And he will be giving a presentation, a 6-minute presentation on the steam calorimeter experiment.
First off, I want to thank Marcus for giving me the floor and introducing me. I'm here to talk about the steam calorimeter. Since we did this project last week, or the experiment, I'm going to spend little time in the background and most time on the results. I'm going to touch on the background a little bit, but mostly I'm going to go over the results and what we got from this experiment. Was it worthwhile? Why we're doing it? Should we do it again? The goal of the experiment is to determine the quality of steam. First, it consists of a separating calorimeter and then a throttling calorimeter. Separating calorimeter has sharp turns in it, 90-degree angles, 180-degree angles, which force the water molecules out of the steam and kind of increases the quality there. Then it enters the throttling calorimeter through a restrictive orifice. Think of it as like a kink in the hose, or the pipe that it enters into the throttling calorimeter is smaller than the pipe that enters into the separating calorimeter. And then at the throttling calorimeter, we're going to measure the temperature and the pressure. The pressure is measured through a pressure tap just right outside. The temperature is measured through a thermocouple that's inside. We assume this process through the entire throttling calorimeter is adiabatic, which basically no heat transfer occurs for our equation. Here is, I define quality. Quality is mass of vapor divided by the mass of the total mixture, vapor plus liquid. Obviously, it cannot be greater than 1, and we would want ideal steam would be closest to 1 as possible. Just pure steam would be 1 or 100% steam, however you want to phrase it. Again, the goal is to determine steam entering the separating calorimeter at position of the experiment. So here's some equations through the throttling calorimeter. We got these equations. This is just the first law of thermodynamics. What it all boils down to, since we assumed adiabatic, there's no heat transfer within the throttling calorimeter, and there's no work done. There's no relative displacement, no translation, no work done. And I define my terms here. And then this is the enthalpy equation, or basically the first law of thermodynamics, just the energy equation, boil it down to simplified. You get your specific heat of the steam is measured at constant pressure, and that would be inside the throttling calorimeter. Temperature is measured through a thermocouple, and the saturation temperature is the saturation temperature at the pressure inside the throttling calorimeter. Let's get to some results. Reminder that when I say 3 or subscript 3, it's entering the throttling calorimeter, and subscript 4 is leaving the throttling calorimeter. So we're trying to find the quality coming through the entire system, which I just thought to the separating calorimeter. The process assumed adiabatic, which, like I said, we can assume that the enthalpy going through the throttling calorimeter is equal to the enthalpy leaving the throttling calorimeter. And then once we have H3 is equal to H4, we can get X3, which is the quality inside or before the throttling calorimeter. And once we get which is the same as the quality after the separating calorimeter, then we can find the quantity entering the first one, the separating calorimeter. Trying not to lose anybody, so save questions for later. I'm trying to speak slowly and clearly, but it all happens the way it happens. And M2 is the mass drain from the separating calorimeter, and M4 is the mass that we come out with the water. And these are all measurable quantities. We can measure the water, we can measure leaving the first calorimeter, we can measure the water after the throttling calorimeter, and that would give us the quality of steam entering the entire process. Now these are my results. This is run one was a little bad, a little shaky. We only got like 15 scans, and so this is run 2, run 3, and run 4. These are really high qualities. That's basically my average, my mean is 90% is steam. 90% or whatever was entering was steam, which whoever that was over there doing group 1 and group 2, I'm pretty sure, we know that it can't be 90% steam because we saw most of the water dripping out of it before the actual experiment. Now, there's some rooms for error. Sometimes you can have a slug of water in the system, like into the steam line, that can screw up your results, but that's not the case here. Like I said, I got ridiculously high numbers for qualities. They're all valid though, they're all between 0 and 1. So another room for error was when I calculated my specific heat value, I interpolated linearly, and it could be that it's not a linear interpolation. My assumption was wrong. And when I also found my temperature saturation inside the throttling calorimeter, I also interpolated linearly from my thermodynamics textbook, which I assumed to be a good assumption, but I might want to go back and double check, maybe even triple check my work. Here's a graph, quality versus time. Since we're the only lab on a Monday, we're the only section, when my task was to measure first time of the day, I realized that if I just do one section, it's not going to do good. So obviously this is February 5th, which is the Tuesday of week before last. We did it 2 weeks ago on Tuesday. And the first lab of the day was 10:30, last lab was 8 o'clock. And here's quality versus outside temperature first time of the day. And then here next to each other. So let's review. We want a high quality steam, so we're not pumping water here, we want steam. Quality varies outside temperature of the day, quality steams increase throughout the day is what I found through my results. And also the distance from the power plant to approximately our lab has an effect. I did not measure this because all the labs were the same distance away from it, but this is just a thought. Thank you all for listening, give me the time. If you all have any questions.
Where did you get the results from?
Where did I get the results from? I followed the lab manual, the equations. For the values that I had to find myself, the constant was specific heat inside the throttling calorimeter. I interpolated from the thermodynamics textbook. I'm pretty sure I used the right table. Like, you know, sometimes they have constant pressure tables, they have superheated read. Obviously I'm using superheated because it's steam. But I'm not sure about that. I would want to double check that.
Also about the steam quality and all that.
Yeah, steam. Yeah. And then I got that through the equations I found in the lab manual, and they're more knowns than the word equation, so I had to find the specific heat value and I had to find the saturation temperature value, which I assumed that my assumptions were good and that my value was good. Because my value I got for quality was in between 1 and 0. If it was out of there, then I would have probably throw everything out and go back. But I compared my quality numbers with a couple of classmates and from different sections, and some I think I had the highest numbers, which I'm not really confident in.
Okay, what about the quality versus time of day?
I got that from the Google Drive from Friday, since we only have this one. Actually the same equations I had, but I used the data from sections 1, 2, 3, and 4 on Tuesday. Whatever sections meet Tuesday, it's one lab at 10:30, one lab at 1:30, and a lab at 4:30, and then a lab at 8. So I figured 4 labs of data will be well worth it rather than just one. But it was all on the internet. I can go over with you. Want me to keep going?
Yes, there is supposed to calculate estimate the Mach number of the fruit of the steam injector.
What's the difference between?
Yeah, I'm doing the steam calorimeter.
He's doing the results from that. He's doing the results.
It's a reporter.
Yes, sir. I'm the reporter, not the lead.
My bad.
It's all right. I need a new pair of shorts. Any other questions? All right, y'all. Appreciate the time.